Yep.
Just one question. I'm still not registering for a class. I'm still waiting for places to do that. Can you talk about that as well?
Okay, let's get started. All right, so this is the second class of CS 411, Introduction to Database Systems. So we're going to be covering the ER model as part of today's class. Before that, some announcements. So for all of your registration questions, go look at tiny.cc/411 FAQ. Other commonly asked answers to other commonly asked questions include there's no wait list, so if you're looking to get on some wait list, there's no wait list. Typically the approach would be to wait and watch if you can to see if you can get into class, and if you have any questions about that process, about overrides, about any of that, go talk to the CS academic office. We don't process any of that information, not me, not any of the TAs. Okay, so this is something that you should talk to the academic office. The website for the class is up. If you didn't catch this last time, it's tiny.cc/411sp17. It's also linked from my homepage. Piazza is up and active. A lot of your classmates have already found team members for the group project. So please go ahead and do that right away. And I have office hours after class today, so if you want to come and talk to me about something specific, please go ahead and do that. A small note about laptop policy. I notice a lot of you have laptops open, and that's totally fine. I usually have my laptop open during class. But if what it means is you're going to be a passive observer as opposed to an active observer, then I would rather prefer that you sit at home and watch the videos. So if you're using the laptop to take notes or supplement your sort of understanding of the material, that's totally fine. But make sure that you're an active participant. If you're a passive participant, I would prefer that you just stay at home, because we have a large enough class that I'll find some students who are interested in the discussion. So that's my feedback to you. And again, you guys are adults, so I'll let you take the decision for yourselves. But this is just something that I've noticed myself. If I keep a laptop open, then I tend to sort of get into the world of whatever, Twitter and Reddit, and get distracted from what's going on in class. Okay, so that's typical for me. Maybe you're different and you find the laptop to be useful during class. That's totally fine. Okay, all right. So that's the last I will say about that. So today's topic. So why should we learn about ER models or ER diagrams? Okay, so let's start by talking about that. So remember in the last class we talked about your group project, which is going to be taking this startup that you are passionate about, maybe Uber, maybe Amazon, maybe Airbnb, and you're building a tiny version of that. Okay, so when you're going ahead and building a tiny version of these companies, how would you do it? Right, the first thing that you would do is you would come up with a conceptual design or a framework for your data, a high-level understanding of what your data needs to contain. Okay, so this is what I call a doodle for your data. Once you have that doodle, you translate that doodle or your design into a format that's understood by the database system, and then you use that format to set up your database within your database management system, or database system for short. Okay, so that's how you would go from an abstract design all the way down to actually setting up your database. And we'll talk about each of these steps in much more detail and much more in much more concrete steps. Okay. After you've set up your database, then you can interact with your data, right? So you can access or modify the data directly via the database system command line. So this is typically for advanced users. Or you can write a host of applications that modify the data resting inside the database. This could be mobile apps, web apps, or other forms or interfaces. Okay, so this is for ordinary user. These are not for advanced users. So this is typically how you would sort of go about building a database management system powered application. Okay, and if you're using the mobile app of Uber or Amazon, you would be typically on step 5. You would not be seeing step 1 to step 4 because that would be happening within the company. Okay? All right. So our focus for today is this conceptual design. So this is the first step, taking your data or your application and abstracting it down into a set of rules or a framework to guide your database design. Okay, so we are going to be talking about this conceptual framework to understand what your data contains or means. So for discussing this conceptual design, we need a modeling language, right? Something that allows us to express what the data will contain, allows us to express the relationships between the data and how that needs to be represented within the database. So this modeling language that is going to be used to express the needs of an application is the ER diagram or the ER model. So what this stands for is the entity relationship model. And it's a fairly popular modeling language. And the output of sort of working through the steps of this ER model is an ER diagram. So you end up with a diagram that codifies the relationships between the various aspects of your data. Okay, so let's start by talking about the entity relationship model, which is the framework, the conceptual framework for describing what your data contains. And as I like to call it, this is like doodles about data. Okay, so it's very pictorial. Okay, so the entity relationship model was proposed by Peter Chen in 1976, so it's quite old. It gives us a language to specify what information the database must hold and how these bits of information relate to each other. Okay, so the concepts that are present within a database and how these concepts are related to each other. So that basically corresponds to the two terms in this title, right? So entities are the concepts, the relationships are how these things are related. Okay, so what we will cover today are the basic formalism of the ER model, how to express constraints within the ER model, how do you deal with weak entity sets, and how would you go about designing a quote-unquote good ER model or ER diagram. So here's an example of an ER diagram, and I'll get into details in a couple of slides, but at a high level you can notice that there are 3 colors and 3 shapes. You have the ovals, you have the rectangles, and you have the diagonals, right? So you have these 4 I don't know what you would call it. You'd call it a rhombus, or would you call it a rhombus? Either way, I'm so used to this shape that I don't even know what to call it. But what would you guys call it? Would you call it diamond? Diamond is good? Okay, diamond. Let's call it a diamond. I wouldn't call it diagonal. That's just sleepy me talking. Okay, so you have these 3 types of shapes, right? Rectangles, diamonds, ovals. And these correspond to 3 types of entities or 3 types of concepts that participate in an ER diagram. Okay, and again I'll get into details as to what each of these shapes mean. Okay, so the first thing that you need to understand is the notion of an entity. An entity is basically corresponds to a real-world object that is distinguishable from other objects. So it's a unique real-world object. And this is described by a set of attributes. Okay, So for example, a company is described by a name and a stock price, for instance, while a product is described by a price, name, and category. Okay? Now, going beyond the notion of an entity, you have the notion of an entity set. An entity set is a collection of similar entities. So you have a collection of products or a collection of companies. These would constitute an entity set. Okay? And each entity within this entity set has a certain set of attribute values. Okay? So for instance, you can imagine that this is an entity set. Okay, so this is an entity set containing products. So you can imagine that there are many little products within there, and each of these products has a certain price, a certain name, and a certain category. These are the attributes for that product. Similarly, for company, you would have a whole bunch of little companies within here. Each of them would have a name and a stock price. Once again, you have the notion of entities. These are sort of unique objects. These are the fundamental primitives. Each entity has a set of attributes, and a collection of similar entities forms an entity set. In this case, you have product as one entity set, company as another entity set. Each of these entity sets contain a bunch of attributes. Have a bunch of entities. Each of those entities contain have corresponding attributes, right? So every product has a specific price, every product has a specific name and a specific category. Okay? Is this clear so far? Okay. So that's the notion of entities and attributes. Then we move on to relationships. Okay? So relationships provide a mechanism for us to relate entities to each other. Let's start by talking about relations in the set theoretic sense. So if you have A and B are sets, the relation R, if you've studied some amount of set theory, you probably know that this relation R is a subset of the cross product or the Cartesian product of A and B. Okay? So that's a relation is defined to be a subset of the cross product or the Cartesian product of A and B. So if you have A containing items 1 to 3, B containing items A, B, C, D, for example, R could contain 1, A, 1, C, and 3, B. This would be pictorially represented as one sort of oval corresponding to set A, one oval corresponding to set B, and the items that are related to each other are joined via these lines. Okay, so this is, and these three lines constitute the relationship R between A and B. So these are the relevant pairs between A and B that are actually related to each other. Okay, so this is the relation R from a set theoretic sense. From an entity set sense, from the ER diagram sense, the relationship notion stays unchanged. Okay, so if I have this diamond here which is makes, then what that makes diagram is indicating is a relationship. This relationship is a subset of the cross product between product and company. Okay, so it's saying that some products are related to some companies, basically. Okay, so that's what this relationship actually means. And I'll get into details as to why this arrow is important in a few slides. But at a very high level, a relationship in the entity relationship diagram sense is just like a relationship in the set theory sense, which is that it's connecting pairs of items that are related. In this particular sense, in this particular example, this relationship is a relationship based on makes. So you would have pairs of product, company, such that the company makes the product. Is that clear? Okay. All right, so back to the diagram. You have entity sets which correspond to rectangles. You have ovals attached to these rectangles. These are the attributes. And you have the relationships, which are the diamonds connecting the rectangles. Okay. So this is the more elaborate example that we saw earlier. You have product, company, and person as the three entity sets. You have these guys as the attributes for product, these guys as the attribute for company, and these guys as the attribute for person. Okay? And then you have product and person related via this buys relationship, product and company related via this makes relationship, and person and employees related, person and company related via this employees relationship. So in some sense, this employees relationship codifies the pairs of person comma company such that the company employs a person. This relationship makes codifies the pairs product comma company such that the company makes a product, and buys codifies the pairs person comma product such that the person buys a product. Right? Any questions so far? Yep.
Does the direction matter, the arrow?
I will get to that in a couple of slides. So the direction of the arrows do matter, and I will get to that in a couple of slides. Any other questions? Okay. All right. So this is where we'll be talking about the directions of the arrows and why it matters. So the arrows signify the multiplicity of these relationships. Okay. So if you have a relationship that's 1-to-1, what that means is you have 1 on the LHS, 1 on the left-hand side connected to at most 1 on the right-hand side, and 1 on the right-hand side connected to at most 1 on the left-hand side, then you have a 1-to-1 relationship, right? Again, this should be a familiar notion to you guys from set theory. In this case, basically, you can clearly see that this is an example of a 1-to-1 relationship because each guy on the left-hand side is connected to at most 1 on the right-hand side, and each guy on the right-hand side is connected to at most 1 on the left-hand side, right? So if, for instance, A was connected to both 2 and 3, it's no longer a 1-to-1 relationship because A is violating that. Okay? So if you have a 1-to-1 relationship, you would basically indicate that by having arrows on both sides of this relationship diamond. Okay, so you would have arrows going into each of the corresponding entity sets. So you can imagine that there's an entity set here and an entity set here, and there would be an arrow going into each of them. Okay, that's how you would signify a 1-to-1 relationship. Let's talk about a many-to-1 relationship. Okay, so a many-to-1 relationship is one where 1 on the left-hand side is connected to at most 1 on the right-hand side, but no such thing holds in the other direction. Okay, so as you can see, each one on the left-hand side is connected to at most 1 on the right-hand side, but if you consider the right-hand side, you have this B guy which is connected to both 1 and 2. Okay, so in this case, this relationship is many-to-1. Okay, so if it is many-to-1 such that everything on the left-hand side is connected to at most 1 on the right-hand side, you would have a diagram which looks like this, where this is the left-hand side entity set, this is the right-hand side entity set. And the arrow goes into the right-hand side entity set. So one way I like to remember this is the arrow in some sense is reducing the, conceptually at least, this is a useful mnemonic for me, the arrow is conceptually reducing the size of the line. Okay, so making it sharper. So you can think of that as being connected to at most 1. So it's reducing the cardinality on that side. So that's one way I'd like to remember this, but it's not, you can come up with your own way as to interpret what these arrows mean. Okay, so the many-to-many relationship is basically you have no constraints. Any item on the left-hand side can be connected to as many items on the right-hand side, and any item on the right-hand side can be connected to as many items on the left-hand side. So these are no constraints. Okay, so in this case, you would have no arrow on either side. So like I said, the multiplicity is shown with arrows. An arrow going into a certain entity set means that that entity set participates in an at most 1 capacity in that relationship. Okay, so if I have an arrow going into this entity set here, that means that this entity set participates in an at most 1 capacity in this relationship. Okay, another way to interpret this going in concept is to use the term determines. Okay, another way to think about this is use the term determines. Specifically, if everything on the left-hand side is connected to at most 1 on the right-hand side, then the left-hand side determines the right-hand side. Okay, because if you tell me that let me give you a concrete example. So let's say maybe I'll get to concrete examples in a second, but at a very high level, this is codifying in some sense a dependency between the left-hand side and the right-hand side, or the right-hand side is dependent on the left-hand side because of this at most one relationship. Okay? Any questions so far? We'll get into examples in a second. Okay. All right. So let's talk about these examples, and I'll ask you guys to help me figure these out. So let's say I have a department head relationship. So it's between an entity set of departments and an entity set of potential people who are department heads. How would you codify this relationship? Would this be a many-many relationship, a many-one relationship, or a one-one relationship? Raise your hand. One-one. Why is that?
Because one department maybe only has one.
Yep. So each department has only one head. Yes, so that's part of it. But each head can be part of at most one department, right? So in some sense, for a one-to-one relationship, you need to think about both directions. So each department has at most one head, and each head is part of, or is the head of at most one department. Okay? What about actor and play? Many to many? Yes. So why is that? Well, because each actor can participate in many plays, and each play employs many actors. Right? So that's the way you would interpret this, the fact that actor-play is a many-to-many relationship. What about employee-company? Yep.
Many one, because there could be many employees for one company, but you can't have many companies for like a pool of the same employees.
Right. So said another way, each company can have many employees, so it's not many one in that direction, but each employee, typically, again, we are assuming this about the data, each employee is part of precisely one company, right? Or at most one company, they could be unemployed. If each employee is part of at most one company, while each company employs many employees, then this is a many-to-one relationship. However, if employees are allowed to hold multiple jobs at the same time, then it's a many-to-many relationship. Is that clear? So basically, each employee can be part of many companies, each company can employ many employees. So it's a many-to-many relationship. Okay. All right. So now moving on from the two-way relationships, what if you had many-way relationships? So you wanted to encode the fact that a purchase happened between the entity set corresponding to buyers, the entity set corresponding to products, and the entity set corresponding to stores. Okay? And you wanted to codify that as a multi-way relationship. So it's not just two entity sets participating. So how do you do that? Straightforward. You just have this diamond and have this diamond connected to these three rectangles. Each of these rectangles corresponds to an entity set that's participating in this relationship. This relationship is called purchase. Okay, so this is pretty straightforward. And so the question is, how would we model this as a mathematical set? This is also pretty straightforward. You would simply consider this purchase relationship to be a subset of the cross product or the Cartesian product between product, store, and person. If you think of these guys as sets, product, store, and person, you can think of this purchase relationship as a path from nodes in each of these sets of length 2, right? So you could have a whole bunch of these paths where I had one path that looks like this, one path that looks like this, or another path that looks like this. So all of these are paths of length 2 in this set diagram. Or another way to think about this is as a subset of the cross product or the Cartesian product of these three sets. Clear? Okay. So now that we know how to model these multi-way relationships, basically what the multi-way relationship means is that there is a certain entity from each of these three sets that participates together in this relationship. Okay, so that's, and you have many such triples of these 3 or 4 entities. Okay, so let's consider this example. So this example is an example of a rental relationship where a person rents a specific movie from a specific video store, and there's a specific invoice which records the rental information. Okay, so this is the 4 entity sets and the relationship. Now let's talk about what the arrow will mean in this context. So you have an arrow going into movie. What would the arrow mean? Yep.
It's a money-to-one relationship.
So what would that mean in words?
There are many people renting one movie, or from many video stores.
So more precisely, so you're on the right track. More precisely, what this would mean is, given a combination of person, video store, and invoice, that is connected to at most one of movie. Make sense? So given a combination of video store, person, invoice, so these are the 3 other sets. These guys, if you consider a combination, a specific combination of these 3 sets, these determine the movie or specify the movie, is connected to at most one of the movie. Okay, is that clear? Okay, so so that's fine. So basically, given a specific combination of video, store, invoice, and person, this corresponds to at most one of movie. But so before we get into the tricky case, let's consider this case, which is, what if I had an arrow going into movie and person? Well, what that means is you can take, yes.
I have a question. So, what if a person rents like several movies, which is in one invoice, or is it just because each invoice has one like transaction ID or whatever?
Let's get to your question in a second. Let me finish this, and then let me finish the slide, and then we'll get to your question. Okay. So, what if I had an arrow going into person? The relationship, again, the arrow, the meaning of the arrow is straightforward. It's basically saying, given a combination of video store, invoice, and movie, it is connected to at most one person. It is determines the person entity. Okay, so that's what the arrow means. Okay, let's go to your question.
My question is basically with the previous example.
Yes.
Just the arrow going to the movie.
Yes.
If a person rents like several movies in one invoice,
Uh-huh.
you normally just do like 3 movies at once or something.
Yeah.
Then how do you? Then why isn't it like? Then why is it at most one?
Good. So your question is, in the real world, a person may want to rent multiple movies on the same invoice at the same video store. So does it really make sense to have the arrow going into the movie here, right, into the movie entity set? No, it does not, right? So in your world, where a person can rent multiple movies at the same time, it would be incorrect to place the arrow here, because that's not the correct conceptual modeling of your world. In my world, where this makes sense, each person is allowed to borrow one movie at a time for whatever reason. Okay? So in that case, it's totally fine to have an arrow going into this. But in your world, where a person can rent multiple movies at the same time, totally fine. Yeah.
Does this also make the assumption that there's only one copy of each movie? As opposed to like if there's multiple copies to a movie, and then that shows that it's the same as the invoice, and one person, or multiple people are renting the same movie.
Okay, so let me try to understand that question. Okay, so does this diagram assume, so let's say with the arrow going into movie intact, does this diagram assume that there's a single copy of the movie, of each movie? I don't think that's the case, because all that it says is, given a person, video store, and invoice, that uniquely determines the movie, but the same movie can be rented by multiple individuals. There's no, at least based on this diagram, there is nothing preventing that from happening.
I mean at the same time.
At the same time, I think that is not prevented by, so I know I'm not showing a lot of details here. Maybe the attributes might specify, for instance, if your movie had a, let's say, your movie had an attribute corresponding to serial number of the DVD or something, then that would uniquely determine the movies. And so so those attributes might specify whether it is one movie or multiple DVDs of the same movie. So there's that aspect. But even beyond that, just the diagram itself doesn't tell me anything about whether your property holds true or not in this world, because it could certainly be the case that there's one copy of every movie, and I wouldn't know that based on the constraints that I've seen so far, or there could be multiple copies of the same movie that are being rented in parallel to multiple individuals, and this diagram would not prevent that from happening, right? So does that make sense to you? So basically it's like the only thing that this diagram says is, given a person video store invoice, there's a single movie that person can rent out. But the same movie can be rented out by multiple individuals, or maybe not. I don't know. That's not part of the diagram. Okay? Any other questions? Yes?
So we kind of just saw there can be like multiple interpretations of like a scenario. Is there any way to encapsulate that into these sort of diagrams? Like, you know how like some people are like, oh, does it mean one movie or multiple movies? Or is that sort of a design choice?
So, so the question is, there appears to be a lot of ambiguity in the interpretation of what a diagram means, and also in translating a real-world description into a diagram. Yes, there is ambiguity, and to a large extent, design of an ER diagram or an ER model is somewhat of an art, because it is encoding to a certain extent. It is sort of, you have to iterate on these diagrams. You have to think about, oh, is it modeling all of the aspects that are important in my application, right? So maybe this arrow is super crucial in my application, and therefore I need to have it, but maybe in some other applications it's not that crucial, and maybe that arrow is not that important, right? If I, by mistake, went and added an arrow when we are in her world and a person is allowed to borrow multiple movies, that would be a flaw, right? That's a flaw in my diagram. So to a certain extent, there are design decisions in coming up with these ER models, but at the same time, there's a clear rationale for every choice that you make that you should be able to justify, okay? Lastly, there is some, even after making the right choices, there is still some ambiguity. There are multiple ER diagrams that are in some sense encoding the same information, and we will talk about how you would pick between those ER diagrams towards the end of the class, okay? So there is still ambiguity, so it doesn't completely answer your question. There's still some ambiguity, but we'll answer it at the end of the class. Any other questions? Yep.
To say that invoice, video store, and person determine movie, does that assume that invoice, video store, and person make up a key?
Let's get to that in a couple of lectures. Or actually, maybe later on in the class we'll come to that, okay? We'll return to the notion of keys. Any other questions? Okay. All right. So one issue with the ER diagram is that it doesn't allow me to encode all of the relationships that I might want to encode. So let's say, for instance, that my relationship or what I want to encode was the fact that invoice determines store. You don't even need to worry about the movie and the person. Just the invoice determines the video store. Unfortunately, the only way I can encode this is by having an arrow into the video store, which implicitly implies that the invoice, movie, and person together determine the video store. Right? So since invoice determines store, definitely invoice, movie, person determines store. Right? So this is not wrong. It's not wrong, but we are losing information. Right? By encoding it in this way, we are losing information. We are losing the fact that just the invoice determines the store. Is that clear? Okay. So, like I said, we are losing information. We aren't clarifying the fact that the store is a function of the invoice only. We are saying that it's a function of the invoice, movie, and person. Yes?
With this scenario, why couldn't you have a separate relationship just between invoice and the video store? Can you clarify this?
Okay. So the question is, if you wanted to clarify this aspect, why wouldn't you have a separate relationship between invoice and video store? That's a great question, right? So why wouldn't you do that? Why wouldn't you have a separate relationship that allows you to encode that information? Maybe you don't have an arrow here, you just have an arrow here. So that does solve this problem in that it makes this aspect explicit. The downside of that relationship is now you have two separate relationships that's encoding basically the same information. Yes, that relationship allows me to encode the constraint better, right? It allows me to encode and specify the constraint better, but this relationship is redundant given this relationship. It's capturing the same information. So given that, I wouldn't want to have two relationships. Again, it's a little bit of a design choice, but in this case, I would still go with an approximate specification of the constraint rather than redundant information. Redundant information is very problematic for databases. So you don't want to encode the same information multiple times. Okay? Make sense? All right. So the next question is, what if I wanted to use the same entity set twice within one relationship? For instance, I might have a purchase relationship with one of the roles that a person takes as a buyer, and the other role is as a salesperson. Okay, so the way I would do this is pretty straightforward. I would just have two arrows or two edges going into this person entity set, and each edge is annotated with the role that that person or that entity set plays in the relationship. Okay, so here there are two roles, as one of the buyer and one of the salesperson. Can anyone explain why we have an arrow going into salesperson but maybe not an arrow going into buyer for this relationship? Yep.
Because you can have multiple buyers of some product at some store by the same salesperson, but one salesperson will only sell a product at some store to one buyer.
Right. So, or said another way, given a buyer, product, and store, there is typically one salesperson, at most one salesperson who is helping that buyer, but given a salesperson, product, and store, that salesperson could have helped many different buyers for that product, right? So this person could be at, I don't know, the shoe department and is helping all customers with shoes. Okay, so this is why you have an edge going into sales, an arrow going to salesperson, arrow going into person for the salesperson role, but no arrow going into person for the buyer role. Okay, another aspect of these relationships or multi-way relationships is that you can add attributes. So this is convenient, for instance, in this purchase example, where I want to add an attribute corresponding to the date of the purchase. This is an attribute that doesn't really belong to any of these other guys, right? So it doesn't belong with product, doesn't belong with store, it doesn't belong with person. It is really an attribute of the relationship. A purchase relationship happened at some point in time, and you want to record that as an attribute of that relationship. So, however, one thing to remember is that you don't necessarily need to add attributes to relationships. You can actually convert this into, you can add yet another entity set corresponding to, let's say, purchase detail in this case, and then have the date be an attribute of that entity set. So it's not necessary to add attributes to relationship, but this is viewed as overkill. There is no need to do this when this attribute could be an attribute of the relationship. Okay, so what this example shows is that it's not necessary to add attributes to relationships, but that is the preferred way. You would typically prefer to have attributes associated with the relationships when that makes more sense. Okay? All right. So, so as it turns out, so we've been talking about these multi-way relationships, right, so far. As it turns out, some ER modeling tools require two-way relationships as opposed to multi-way relationships. They don't admit multi-way relationships. So the question then becomes, do we need multi-way relationships, or do two-way relationships or binary relationships suffice? So let's say I have a multi-way relationship that looks like this. How would you guys think about converting this into binary relationships? Any ideas? Yep.
You could make sort of a minimum spanning tree of relations.
A minimum spanning tree of relations. I'm not sure what that would entail here.
Or just like a path that hits all the entities.
Interesting. That's a very creative solution, but I think it will miss out some of the aspects, because it's not, so intuitively, so if you have, let's say, product connected to store connected to person, you would be missing the product to person relationship, right? So you don't want that to happen. So a path will not suffice. We need something, but we need something else that will encode the same thing. It's not that complicated. Yes?
Like, it's sort of building off the idea of a tree. You could, like, have multiple purchase relations and then have, like, sort of like a root sort of entity, and then it goes down to what you need it to.
Okay, that's another creative solution, but I think, so what he's saying is, can you consider maybe like multiple purchase relations and connections between them that are encoded in some form of a tree, such that you can then encode the relationships between each of these relations within this tree and the store product person? Maybe, but there's a simpler solution, and let me tell you the simpler solution. So the simpler solution basically says, I'm going to take this purchase guy and I'm going to convert the purchase into a relation. Okay, so that's the first step that I'm going to do. I'm going to convert this guy into a relation, and this relationship, this relation is going to have date as an attribute. Okay, so once you convert purchase into a relation with date as an attribute, then all I need to do is to have relationships between product and purchase, relationships between purchase and person, and between store and purchase. Why does that make sense? Well, this is because the purchase, the relationship, can be encoded. So the notion of a relationship, so this concept of a subset of the cross product of product, store and person can be itself encoded as information, can be itself encoded as an entity. That entity or that entity set is connected to these other entity sets. It's connected to product, it's connected to store, and it's connected to person. Okay? So what I would do is I would take this purchase diamond, this relationship, convert it into an entity set with attribute date, and then have these relationships with product, store, and person. Question here, why do I have these arrows? The reason why I have these arrows is because each purchase is associated with at most one product, each purchase is associated with at most one store, and is associated with at most one person. Okay, because that's what we got from the previous encoding, right? Each purchase is associated with one person because that a purchase was a multi-way relationship earlier. It was associated with a single combination of product, store, and person. It was encoding a multi-way relationship earlier, so I'm breaking down that multi-way relationship into an entity set and a bunch of many-to-one relationships. Is this clear? Okay. All right, so this is the notion of relationships. We talked about how this has relations, or how this is related to the notion of relations in the set theoretic sense. We talked about binary and multi-way relationships. We talked about constraints on the degree of the relationship and converting a multi-way into many binary ones. We talked about attributes of relationships, which are not necessary but are certainly useful. Okay. Now some other special cases. Beyond the single notion of an entity set, you could also have subclasses in some contexts. These are often useful. So for instance, if I have a product entity set of which some of these products are software products and some of these products are educational products, then the way I would do this is to have an entity set here, and then I would have a triangle here with an is a note associated inside, and then and then this is associated with, or this, you can think of this as a hierarchy with this guy being the root node, and then you follow this path down to this entity set, which is a special case of product, which is a software product, and the software product entity set has an attribute called platforms, while here's another example of a subclass. You have educational product, which is another entity set, which is a subclass of products, again following the tree structure, with age group as an attribute of educational product. Okay, so one thing to remember here is that this is not like subclassing in object-oriented languages, because a specific entity can belong to multiple classes here. So for instance, let's say I have products A, B, C, D, E. I might have B, C, D as software products, A and C as educational products, right? So you have C, which is in common between software and educational products, and also belongs to the root by default, right? So, and the way to think about this is, for this product number C, you would be grabbing the attributes corresponding, the basic attributes corresponding to product, which is price, name, and category, from this entity set. You'd be grabbing the software product related attributes from this entity set, and the educational product attributes from this entity set. Okay, so C is an object or an entity that belongs to all three classes or all three entity sets. A, on the other hand, belongs to just product and educational product. D belongs to this guy and this guy. E only belongs to product. Okay, and that's totally fine. Does it make sense? So going over this one more time, Isar triangles indicate the subclass relationship. They point to the superclass. The subclasses form a tree. There's no multiple inheritance. There's no not a DAG. So why do we want subclasses? The reason for why we want subclasses is because consider one way to represent a subclass as, or get rid of these subclasses, right? So one way to get rid of these subclasses is to maybe add an attribute corresponding to platforms here, maybe add an attribute corresponding to age group. Let me erase these guys, there's too many annotations. Okay, so one way to get rid of these subclasses is to maybe add an attribute corresponding to platforms, maybe add an attribute corresponding to age group, right? And then maybe you might be able to get rid of these guys, right? You might need additional attributes, but for certain you need both of these attributes. Yes?
Would we also not need like a type of product to know whether it's...
Good, yes. So the question is, would we not need a type of product attribute or some other annotation as to whether it's a software product or an education product? Absolutely. So like I said, these two are absolutely needed, but you might need additional ones. You might want is a software product or is a educational product, right? As maybe Boolean attributes, right? You might want, so in some sense you have these 4 attributes that you need to encode for 4 additional attributes that you need to encode for every product. The downside of adding all of these attributes to the main class or the main entity set, or the main class in this case, is that often these platforms and age group attributes are unused, right? So if you have products that are neither software products nor education products, these other attributes are unused. Okay, so it's kind of wasteful to have these additional attributes be part of the main class. So it's often preferable to have subclasses that capture the special case attributes, okay, so that you can have it restricted to the subclasses as opposed to the main class. So that's the rationale right now. We will revisit once again this subclassing aspect when we talk about the translation of an ER diagram into database systems context. But for now, all you need to remember is the fact that adding attributes to the main class leads to wastage, leads to attributes that are often unused. Okay, so yes.
Question. So I believe in one of your slides you said the direction should be pointing to superclass. I don't see any.
So there's no okay. So there's no direction here. It's just that the tip needs to be connected to the superclass. Yeah. Okay. So brief note, like I mentioned about ER versus object-oriented subclasses. In the object-oriented world, objects are in one class only. Subclasses inherit all of the properties of the parent class. That's not true here. ER entities have components in all subclasses to which they belong. So like we saw here, a product can be a product, an educational product, and a software product, right? It could be all of these and could have attributes corresponding to each of these three entity sets. Okay, so that's the notion of subclassing. Here's another example. So here I have movies, animation movies, and murder mysteries, and these two are subclasses of movies. As an example, the minions might live here, might live here, and might live here. I don't know. Mad Max Fury Road maybe lives here, and maybe not in either of the other ones. And then Orient Express maybe lives here and lives here, but it doesn't live there. Okay? And another thing to note is that I could have relationships starting from any of these subclasses. So these subclasses behave like regular entity sets. So the animation movies could have a relationship with stars who are providing the voiceover for the animation movie. Yes?
So are the subclasses represented as like an attribute? So this is a subclass in which this movie resides, and then something blank, or how would you?
Okay, so the question is, how would you represent a subclass in this context or in general? In general. Okay, so we will revisit how we represent subclasses within the database. The translation for subclasses into database concepts is actually a little murky, and we'll talk about the various alternatives in a couple of lectures, maybe in the next lecture, in fact. But for now, let's just try to model it in the most faithful way possible. We will revisit that question. There are multiple options. One of the options, like you mentioned, is representing it as an attribute. Another option is to represent it in an entirely different structure. You could separate out all of these concepts and place it in a separate relation, if you will, in the database context. But let's not get into that for now. Okay, we'll revisit that. I promise you. Yep. Certainly. Yep. So you could have, so for example, this relationship is encoding voice-over relationships, right? While you could have another relationship here, which is encoding the starring in-person relationship, right? So this star actually had a physical form in this movie or whatever, right? Not just contributed their voice. And that's totally fine. You could have multiple relationships between entity sets and classes, or entity sets that share a subclassing relationship. That's totally fine. Okay? Cool. So now that we've done with subclassing, let's talk about constraints, and we'll revisit this notion of keys that one of you brought up. So a constraint is basically an assertion about the underlying data, the database, that must be true at all times. And constraints, or these properties that hold true of the data at all times, are part of the database structure. They are part of the schema, if you will. Okay? And therefore, they must be part of the ER diagram as far as possible. There may be some constraints that you'll never be able to encode within an ER diagram. For example, one of the constraints that you guys brought up, which was no two individuals can rent out the same movie at the same time. Maybe that might be hard to to encode within an ER diagram, but we'll talk about how we may be able to do get pretty close in a few slides. Okay, so yes, we may not be able to capture all constraints, but ER diagrams allow you to capture constraints. These are constraints that are part of the database framework, they are part of the database structure, they are part of the schema. Okay, and they are absolutely important in database design. So there are commonly used constraints. The commonly used constraints are keys. So these are attributes that uniquely identify entities in an entity set. For example, for a person entity set, the social security number uniquely identifies an individual. And then you have referential integrity constraints, which are basically relationship-based constraints. So, for example, one type of a referential integrity constraint is if you work for a company, then it must exist in the database. Okay, so this is a constraint that is colloquially referred to as no dangling pointers, right? So if you are working for a specific company, then it must exist in the database. If you've bought a specific product, then that product must exist in the database, and so on. So there are other forms of constraints that are not easily captured within the ER diagram. The textbook has more examples of constraints that can be captured within an ER diagram, but we won't be covering the full generality. We might want to have domain constraints like people's ages are between 0 and 150, other forms of general constraints like at most 50 students enroll within a class. Okay, so these are all useful. We won't be able to capture a lot of these constraints within ER diagrams. So why are constraints important? Well, they allow us to understand properties of the data better. They give more semantics and more meaning to the data, so it's important to understand and know them. It also allows us to model the data more faithfully. If we know that a person can borrow only one movie at a time, it is useful to know that so that we can explicitly model it. It allows us to refer to entities. So for the keys constraint, it allows us to uniquely specify which entity we are talking about. Constraints are also important because they allow us to do efficient storage, data lookup, and so on. And this won't be a focus of the next few lectures, but we'll revisit this in the latter half of the class, of the course. Okay, so how do we represent keys in ER diagrams? So we're going to be focusing on two types of constraints, keys and referential integrity constraints. So keys in ER diagrams are represented using an underline. So for instance, for the product entity set, I've underlined the name and the category. So what that means is the name and the category together uniquely determine the product entities. Okay, so they together uniquely determine the product entities. So that's the notion of a key. Both of these attributes are part of the key of this product. In this case, you have a person entity set, and the SSN is underlined. So the SSN is the key for this this entity set. The SSN uniquely determines the person entity. Here, notice that there may be, in some cases, it may be possible to say that the name and address uniquely determines the individual, right? So maybe together the name and address are able to uniquely determine the individual, so you don't really need to use the SSN. So this gives us so this brings us to the issue that there may be multiple keys for the same entity set. One decision that we make in the ER diagram is to pick one of these keys, so we don't represent all possible keys. We pick one of these keys. In this case, I've chosen to use the SSN as the key. In other applications, I may choose to use the name and address together as a key. That's totally fine as well. Okay? So, like I said, there's no formal way to specify multiple keys in ER diagrams. You just pick one and go with it. So a key can consist of more than one attribute. Every entity set must have a key because the entity set is a set of uniquely identifiable entities. So in the worst case, if you consider the entire set of all attributes, that will constitute a key. Okay, so in the worst case, you take all of the attributes and underline them, that will form the key for the entity set. But typically, the entity sets have fewer attributes that form the key. Also, there can be more than one key for the entity set. The key that is underlined is known as the primary key for this entity set. This is the key that we think is most important for the entity set. For example, in the person relationship here, a person entity set, I underlined SSN. That's a primary key. It's a key that is the most important for this entity set. Okay, so there's more on keys is a hierarchy, but I'll let you look at that in the textbook.
So for the product class, it has two keys, which are like name and category. So are they both primary keys?
Okay, so no. So in the product case, when I have underlined, so let me erase all of this. In the product case, when I've underlined both of name and category, what that means is name and category together is a key, not separately, right? So if name and category both were individually keys, then I'll have to pick one. I can't pick both and show them the ER diagram. So the fact that both of them are underlined means that they together are the key. So name and category together form the key. Okay. Right. So the other form of constraints are referential integrity constraints. These are the equivalent of don't allow dangling pointers. Referential integrity constraints on relationships explicitly requires a reference to exist. So what does that mean? Well, for example, for every product, you want at most, so far we've had this arrow which indicates at most one, right? So every product must be related to or is made by at most one company, right? But it would be totally weird if a product was not made by any company, right? So you want not just at most one, but you want exactly one company to make a product, right? So the way to encode that is to use a semicircle here. And so what the semicircle means is exactly one. So every product must be made by exactly one company in the database. So an arrow means at most one. A semicircle means exactly one. So here's another example. So I have movies and studios and presidents. I have a semicircle here and a semicircle here. What this means is every movie is owned by exactly one studio, and every president runs exactly one studio. Right? It would be weird to have a president who is not the president of any studio, right? So that doesn't make any sense. Okay, so also related to this notion of increasing the power of the modeling framework. So just like subclasses increase the power of the modeling framework, weak entity sets also allow us to increase the power of the modeling framework, and we're describing that in the context of constraints because that's where they are important. So entity sets are weak when some of the key attributes come from other classes to which they are related. Okay, so for example, let's say I have two entity sets, team and university. In this case, the team is a weak entity set, and this weak entity set is connected via this relationship to this regular entity set. Okay, so the reason why this team is a weak entity set as opposed to an entity set is because the sport and the number, these are the attributes for the team, do not uniquely determine the team. Okay, the team also requires an attribute from one of these relationships. These are called supporting relationships to describe the entities of this weak entity set. Okay, so like I said, the sport and the number don't uniquely determine the team. The football team number 1 may be present multiple times in this relation, in this entity set, right? So you don't want you don't want to be not able to distinguish between them. So fixing this by saying the sport, the university name, and the number together determine the team is one way to uniquely identify entities corresponding to team. And the way we do that is via the supporting, you designate this guy to be a weak entity set, you have a supporting relationship, and you have another entity set here. This is connected via this semicircle, so it's a referential integrity constraint. So it's saying that each team is associated with exactly one university, and the university has a specific attribute that the weak entity set borrows. Okay, so the weak entity set here is uniquely determined by the combination of sport, number, and name, not just sport and number. As another example, so if I wanted to say that CS411 along with the University of Illinois, or UIUC, determines the rest of the attributes, for example, the title of the class, then the way to do this would be to have the course as a weak entity set. I have a supporting relationship, which is offered at. I have a semicircle corresponding to the other entity set that it's connected to. And in order to uniquely determine a course, I would need the attribute that's underlined for the course, which is number. So this may be CS411 for one particular entity, and the university name, right? So it's the attribute that's underlined in the supporting entity set. Okay, so this would be UIUC, for example. Okay, so these two guys together, CS411 and UIUC, together determine the title of the class, which is database systems. Okay, does this make sense? So where does this weak entity set, or actually before that, let me recap what I have here. Occasionally, entities of an entity set need help to identify them uniquely, like in the case of the courses, you needed the university name to be able to identify which course we were talking about. An entity set is weak if in order to identify the entities of E uniquely, we need to follow one or more many-to-one relationships. It's not even just a many-to-one. It's a many-to-one with exactly one, not at most one. Many-to-one relationships from E and include the key of the related entity sets. So all of these supporting entity sets, you steal their keys in order to be able to determine uniquely the entities of this weak entity set. So note that this is not a subclassing relationship because these guys are not subclasses, right? So the team and university are not subclasses of each other. Course and university are not subclasses of each other. They are not the same type. These are completely different entities. Okay, so notations for this: university is a supporting entity set for team. Affiliation is a supporting relationship for team, right? So here's a case where weak entity sets very naturally arises. So you have a multi-way relationship like we saw earlier, and we were converting this into a collection of two-way or binary relationships. In this case, remember that this was what we had, right? What we had was you had a relationship, you had an entity set corresponding to the relationship purchase, and then you had many-to-one relationships going into each of these entity sets. So here, notice that it's not sufficient to identify a purchase using just the date, right? You need more attributes to identify a purchase. In particular, you need the attributes corresponding to product, store, and person in order to identify the entities of the purchase entity set. Therefore, the purchase entity set is a weak entity set, okay? And it has three supporting relationships: product of, store of, and buyer of. And these three are, you have exactly one relationships with three supporting entity sets: product, store, and person, whose keys in this case are name and category for product, address and name for store, and SSN for person. So in order to uniquely identify a purchase, you would have the following key: name and category for product, address and name for store, and the SSN. These 5 attributes uniquely determine a purchase. That makes sense? Any questions?
So
Yes.
the fact that those keys determine the entity, which is a subclass of purchase, then they also all determine the superclass.
Okay, so so these are, we are talking about weak entity sets and not subclasses or superclasses. But what was your question again?
So pretty much all the attributes that are keys to like product, store, and person, all of them together form the key to purchase.
Yes, exactly. So for a weak entity set, in order to determine its key, the rule is follow all of its supporting relationships, steal all of the supporting entity sets key attributes. That forms the key for the weak entity set. So like in this case, starting from this weak entity set, I went in all directions. These are the 3 directions for the supporting relationships. I went and stole these attributes here, these 2 attributes here, and these attributes. So I have these 5 attributes that constitute the key for the purchase entities. Okay, and with that I'll stop. I have a few more slides, but I'll cover that in the next lecture. Okay, see you guys on Wednesday.